Good evening. We will be seeing what we were trying to do yesterday, and there were few questions which I answered yesterday, but the answers were not very clear probably. So we will see briefly and then continue the presentation. Now, what we are trying to do is to define the efficiency of an electrochemical energy conversion device. Okay. The maximum efficiency that can be realized is depends upon the electrochemical thermodynamics, that is delta G. Okay, delta G of the electrochemical reaction, that is the maximum efficiency that we can get. We will see little later what is the maximum efficiency. Whereas the real efficiency is what is the rate at which the reactions take place at the electrode surface. For example, the whole of the delta G may not be taking place in the same rate at the to the completion. Okay, so therefore the efficiency will be less. So therefore the real efficiency of an electrochemical energy conversion device is controlled by the electrode kinetics, the reaction taking place, the rate of the reaction taking place at the electrode. Whereas if I have an ideal electrode, all the rate will be the maximum, and it will be the efficiency, the maximum efficiency will correspond to the electrochemical thermodynamics or the free energy of the reaction. Now, quickly looking at it, the fact that the real efficiency are less than the ideal efficiencies instill interest in understanding the fundamental theory of governing this electrochemical conversion of chemical energy to electricity. Since the efficiency that will be obtained from an electrochemical device will not be the maximum. Maximum is the theoretical efficiency. The electrode kinetics controls the efficiency of the operating system. The operating system's efficiency will be less than the maximum efficiency. Therefore, we want to understand the electrode kinetics and optimize the electrokinetics to the optimal level. Now, the power per unit weight as well as the efficiency are important factors to be considered. We will see later on what is this. Since the power is the rate of producing energy, the kinetics of electricity producing interfacial charge transfer reaction, that is the electrode kinetics, becomes important. That is why we are going to see the electrode kinetics. Now, the fuel, if I were to take the fuel, let us take only 1 and 3. Okay, the 2 is only a modification of 1. So if I take this 1 and 3, the fuel is combusted to produce the steam. The steam is used in a steam turbine. Then it generates a generator. Then it is converted to electricity. Whereas in the fuel, in an electrochemical reaction that takes place at the electrode surface, it is directly converted to electricity. Here is the problem that is there. The efficiency of this will be, for example, if I will assume that I have a fuel which is 100% combustible, but only 50% is combusted here. Okay, that 50% will be only used in the steam turbine. 50% of the steam that is produced is used in the steam turbine. So therefore, the steam production itself is 50%. Out of the 50% of steam, only the turbine is using 50%. Therefore, 0.5 into 0.5 only, the 0.25 only will be the efficiency of the after the steam turbine. And if the generator is another 0.5, then 0.5 into 0.5 into 0.5, that is the electricity that you can produce. Whereas if I take fuel and put it in electrochemical fuel cell, then it is converts 50%, then the 50% electricity will be there. Okay, we will explain it in a minute. And what is this efficiency? Why it is a product function and not an additive or is a subtractive function? So therefore, what is in any electrochemicals energy system, energy conversion to electricity, the reactions of importance are all given here. The 15 reactions and also another 30 reactions. Only temperature is different. we will not worry about it. The parameters of important is delta G and the number of electrons and the maximum voltage that you can get. For example, H2 plus half O2 giving rise to H2O, the maximum voltage that we can get is 1.229 volts, but actual volt that you will get will be 0.830. Okay, when you are drawing a current, this is what is the efficiency. Now you can see 0.8 by 1.3 is the efficiency. Okay, all other parameters we will see later on. The temperature coefficient of potential, the delta N, the change in the electrochemical reaction, how much of the delta N. I hope you have already studied some equilibrium thermodynamics. It is delta N is the number of molecules that are changed from going from reactants to the products. So now, if all these reactions are of very great importance, I have summarized or I have gathered all the data for you. Therefore, you can keep these two tables for your reference. Now, conventionally, thermodynamic parameters like free energy, activity, equilibrium constant, temperature, and pressure, all these parameters depend upon the cell potential and its coefficient with experimental variables. It is already known to us. Equilibrium constant is dependent upon the temperature, pressure, etc. So now the efficiency of an electrochemical energy conversion device, the epsilon, is given by delta G by delta H. If I were to substitute with delta G as delta H minus T delta S, then it will be 1 minus something. Okay, so this is how it becomes less than 1. 1 minus something is but it all depends upon the delta S, the magnitude and sign of delta S. If delta S is positive, then the efficiency will be less than 1. If the delta S itself is negative, then efficiency will be greater than 1. It is perhaps not appropriate to regard this equation as indicative of intrinsic maximum of less than 1 or less than 100%. That is not true. In electrochemical energy conversion device, it is possible that in some reactions delta G can exceed delta H. Delta G can be greater than delta H, therefore the efficiency can be greater than 1. For example, you take CO plus oxygen giving rise to CO2, the number of products molecule is 1, number of reactant molecules 1.5 or 1 or 2, therefore the delta G will be a negative quantity. Therefore, it will this term will become positive. Therefore, it will be efficient as. So, if you take this reaction, okay, this reaction. If I take this reaction, you can see the maximum voltage can be obtained is 0.782, but the realizable voltage is 1.372. Let's say C plus half O2 given as CO2, CO. C plus O2 giving rise to CO2 also is delta N is 0. Therefore, the potential will be the potential, maximum potential and realizable potential will be equal. CO plus half O2 giving rise to CO2 minus 0.5. Therefore, you can see the potential will be like this. The cell voltage E under load is less than the thermodynamic reversible potential. Thermodynamic reversible potential is when the current is not drawn. Okay, let us assume like that. Okay, when it is an open circuit, the maximum potential that can be is, for example, if you take a hydrogen oxygen fuel cell, then the potential can be 1.23 volts. The reasons for this difference between E, the potential that you have, for example, 1.23 here, the 1.23, but 0.83 is the realizable potential. This difference in the potential, the E is the realizable potential, ER is the reversible potential. The voltage efficiency, E epsilon V, is given by E by ER. The voltage efficiencies are maximum at low current densities, with the limiting value is reached. Okay. In the same way, the Faraday efficiency is E epsilon F, okay, is I by IM. IM is the theoretically expected maximum current on the basis of the reactants consumed, assuming the overall reaction goes to completion. it never goes to completion. Therefore, I will be smaller than Im. Faraday efficiency is analogous to current efficiency. E of Faraday may be less than 1 because of other reasons. Not only this, parallel electrochemical reactions yielding fewer electrons per mole of the reactant consumed, chemical reactions of reactants catalyzed by electrodes, direct chemical reaction of the two electrode reactants. Electrode, for example, zinc, if take zinc will react to give rise to zinc plus 2 ions, copper electrode will be giving rise to copper deposition. Such cases, the current efficiency will be different because you are generating more ions than the depolarizer or the electrolyte ions. So the overall efficiency is epsilon is a product of the individual efficiency, current efficiency, voltage efficiency, Faraday efficiency. Under definite experimental conditions, T and P, epsilon I is a defined quantity. Epsilon I is the current efficiency. The maximum value of epsilon will be equal to epsilon I if E is the theoretical. The maximum effort in electrochemical devices or converters is to make the other two efficiencies, voltage efficiency and Faraday efficiency, as one. Then there is a thermal and electrical efficiency. We need to emphasize, optimize all these parameters. There was a question why efficiency is a product function, not an additive function. This is the question I was referring to. Now let us the example I gave yesterday is the same example I am taking. Let us assume that water is flowing in a canal, and we are interested in the amount of water that is available at the end of the canal. Now in the canal, let us assume that I have two blocks. The first block is at a distance of 1 mile, and the second block is at the end of the second mile, and we are measuring the water that is flowing in the canal after the second mile. So in the first block, 50% of the water is overflowing, and 50% is retained in the first block. So the water flowing from the first block will be only 50%. Now out of this 50%, if another 50% is blocked by the second block, the efficiency of the second block is 0.5. So the 0.5 of 50%, because only 50% of water is coming into the second block, out of it 50% is going away from the second block. Therefore, in the first block 0.5, the second block 0.5. So 0.5 into 0.5 will be 0.25. So therefore, at the end of the second block, the amount of water that will be flowing will be 25% of the total water that is present, because 50% of the water is contained in the first block. Then 50% of the water coming to the second block is contained in the second block. Therefore, only 25, the total water that will be available in this after the second block is 0.5 into 0.5. This will demonstrate the efficiency is a product function, not an additive or a subtractive function. So then we have also talked about the overpotentials. We are going to introduce a new term here, which is very great significance in the electrochemistry, which is called the exchange current density. So when we are dealing with the exchange current density, we have to talk about something about overpotentials. We have already told that I will, at the appropriate time, we will talk about the overpotentials. We will tell the overpotential here. Okay, when electrons or metallic ions pass through the interface of a simple electrode, thermodynamically defined electrode reversible electrical potential irreversibly is set up. If the open circuit potential, the equilibrium involved in is a dynamic one, and the rates at which charge carriers pass through the interface is neither direction are equal. In other words, the exchange current density I0 is the same in both directions. If the anodic and cathodic partial current densities are respectively denoted by I plus and I minus, then at equilibrium I plus will be equal to I minus, that will be equal to I0. Therefore, I0 is not zero. Exchange current density is a fixed value, but only thing is it is the equilibrium value in the respective electrodes, I plus and I minus, or you can say assume that it is anode and cathode, whichever way you want to look at it. exchange current density, why we are worried about exchange current density? There was a question on this parameter I0. We shall try to qualify this term exchange current density later on, but we have defined the exchange current density today, that is equal to the anodic current and the cathodic current when they are equal. When there is an anodic current and a cathodic current, we both have magnitude. The same way, exchange current density also has a maximum, is a magnitude. I0 is a number, current density. Okay. The use of this exchange current density, for the moment we will take it up. The value of the exchange current density is the maximum current that one can draw from an electrochemical device when equilibrium is established. But in an electrochemical device, we are never looking at the equilibrium situation. Therefore, the exchange current density, realizable exchange current density, and the theoretical exchange current density will be different. We will look at them little later. This exchange current density has a value. So, for example, in this picture that I didn't show it yesterday, at the very lowest current, very near to zero, the potential that is available is the thermodynamic reversal potential 1.23 volts for the hydrogen oxygen reaction. But at very slow currents, okay, say assume that it is 0.1 milliamperes per square centimeter or current density, the potential already is nearly 0.9 or 1 volts. And this is called the activation over voltage, and this region is called the concentration over voltage, and the steep down is called the diffusion over voltage. Okay, we will see all of them. Over potential may be observed when an additional external current is superimposed on the system by means of a suitable counter current. For example, you take this picture. Here there is a zero current. When I draw some current, the potential drops down. That is what it means. So therefore, if I want to get this 1.23, I have to apply this balance of potential. Then only what is reliable potential is nearly 0.9 to 1 volt, but I have to supply 0.23 volts to get this is the potential that I can draw when the current drawn is zero. For example, during electrolysis or during withdrawal of current from a galvanic cell, the electrode will then assume a potential EI, which will differ from the equilibrium value to an external extent governed by the current density. The difference between EI and the equilibrium reversible potential is known as the electrical over potential, which is generally denoted as eta is equal to EI minus E reversible. When no thermodynamic equilibrium potential is established for zero external current, the difference in the potential I is equal to zero and IC is not equal to zero is termed as polarization. This is a polarization curve. Because here we are drawing some current. You can see the potential is drawn as a function of the current. The x-axis is the current density, y-axis is the potential. So eta is EI minus E0. In some cases, E0 is equal to E reversible, that is the polarization, and over potential are equal to each other. E0 is not equal to E reversible. You realize whenever electrode potential is called mixed potential. We are going to talk about mixed potential later on. We will keep it for the later on. Over potential and polarization are determined with the aid of a suitable reference electrode. Their usual reference electrode is column electrode. We will show you the column electrode construction. Okay, one has to construct a column electrode. Today you are always buying the electrode, and I think it is good to buy. I am not saying that you should, but the concentrations of the material must be, an activity must be unity. We will come to it later on. They are connected to the electrode and the test and the galvanic cell. The voltage of such a cell is then measured in the presence and in the absence of the polarizing current. When there is an absence of the polarizing current, that is irreversible. Two values are obtained whose difference is the over potential or the polarization respectively. The over potential, which is generally positive when experimental electrode works as anode, and negative when the external electrode is when I is less than 0, I greater than 0. Will generally assume a stationary value after an initial period of adjustment. A plot of these stationary values of eta as a function of I is termed as the over potential current curve. We are going to use all of them. The over potential current curve, the slope of that is known as the polarization resistance, the initial slope. Okay, we'll take up the y initial slope. What is the slope at any current value and all those things. Okay, at any current value, the current can be due to the electrochemical reaction or the impurities or the electrode reactions. That is why we are taking the slope at the initial point. Since the charge E is equal to 8, the polarization capacitance per unit area is defined by this. So that is the initial capacitance when T is equal to 0 is identical to the capacitance of the electrochemical double layer. We'll show you a picture in a minute. The over potentials can be ascribed to three principal causes. I have only put three of them. There are many more. We are not talking about them. In all these things, we will incorporate them as subsidiaries of them. During the passage of the current, the activities or concentrations of the reactants near the electrode surface undergo a change, resulting in the corresponding alteration in the equilibrium electrode potential. The electrode potential is the potential that is available on the electrode and the potential available in the electrolyte. So this difference only is what is called the potential, electrode potential. The additional over potential may be required to enable the charge carriers to cross the interface. That is the transition reaction. Transition reaction is electron transfer from the electrode to the electrolyte or electrolyte to the electrode. The incorporation of atoms, for example, you take copper 2 plus ion getting deposited on copper, then it is the copper 0 has to get into the lattice. So this is called the resulting over potential is called the crystallization over potential. The observed over potential eta may thus be resolved into three additive components: the concentration over potential, the transition over potential, and the crystallization over potential. Within this, you can have varieties of them. We will see all of them later. Yesterday, I have explained this. Anyway, we will see eta C can be the concentration over potential can be just now I told you concentration can be diluted by if the reaction produces water. So therefore, concentration polarization can be due to the electrochemical reaction and the concentration gradient between the electrode and electrolyte. So the transition over potential and the crystallization over potential. The concentration over potential is can be further subdivided into diffusion over potential and reaction over potential. Okay. The diffusion over potential is caused by the depletion of the enrichment of the reactants at the electrode surface. For example, silver nitrate solution is electrolyzed using silver electrodes. The silver is dissolved from the anode and gets deposited at the cathode. The total concentration of silver Ag ions remains unchanged throughout. But at the electrode-electrolyte interface, an increase in the concentration of silver ions will, however, be observed at the anode, while a corresponding decrease occurs at the cathode. The overall concentration remains the same. Even when the electrolyte is vigorously stirred, concentration gradients of this type within the layer adhering to the electrode may only be overcome by diffusion. To understand the cause of reaction over potential, okay, reaction over potential, it should be realized that the potential determining transition state may be preceded followed by chemical reactions whose rates are lower than its own. The equilibrium concentrations required to produce irreversible will not be established in time. The slow step may therefore be regarded as inhibiting for the establishment of irreversible. Crystallization over potential is treated as a special type of over potential and is observed when the inhibiting step consists of addition of metallic ions to crystal lattice or their separation from it. Copper ion deposited in copper, or zinc dissolving as zinc plus. The resistance over potential corresponds to the ohmic potential drop at the electrode and can be due to the presence of surface films. For example, as soon as I dip an electrode, a film will be absorbed on the thing. Therefore, this film will give rise to a resistance at the electrode. That is called the resistance over potential. The total over potential is sum of all these things. Some of them may be zero, some of them may be very high, or all of them will have numeric values. Yeah, transition over potential, crystallization over potential, diffusion over potential, reaction over potential, resistance over potential. So the resistance polarization, yeah, and the transition over potential are characteristic of reversible reactions and therefore collectively called reversible over potential, irreversible over potential. Okay. Whereas the ohmic over potential or the diffusion over potential and the reaction over potential are collectively known as the reversible polarization because they are reversible. Activation over voltage is the, we have already seen this. This portion, okay, the initial portion, okay, this portion is activation over voltage. Activation over voltage is loss caused by the charge transfer of any material or process that has limited speed. This activation over potential results from slowness of one or more of the intermediate steps in either one or both the electrode reactions. It can be anode, it can be cathode, in both. The open circuit voltage ED is generally less than the thermodynamic reversible potential for the specific conditions of temperature and pressure. Activities of the reactants. We have to say the spelling of the reactants is wrong. The activities of reactants, activities, not the concentrations. Since we do not determine the activities, therefore we are we are assuming at the dilute solutions activity will be equal to concentration. We have to understand the activity and concentration. At some point, at some values of the concentration, activity will be more or less equal to concentration, but not always. So we have to understand this. For example, take a human being, the activity can be different from the real efficiency of the person. Products, and because of the interference caused by advantageous reactions of impurities. When the net current drawn from the cell is small, cell potentials may tend to be controlled by the impurity reactions. However, due to their low concentrations, impurity effects are small at higher currents generated from the cell. When I draw very high current, it is due to the depolarizer, the electrochemical reaction. Whereas when I draw very low current, it will be only the impurities will be reacting. Further, it is found that at low current densities, there is a very sharp decrease in the E with I. That is what we showed this in the figure. This type of behavior is characteristic of highly irreversible process and is caused by activation over potential. The limitations can generally be overcome by employing an activation catalyst or by increasing the temperature. It is already known for us. The concentration over voltage, it is the voltage. It is the voltage difference caused by diffusion process due to pressure gradients and changes in the utilization rates of gases or liquids. The delay causing in reaching the steady state conditions or the absence of equilibrium conditions as a result of the current flow, using up or producing materials are sources of concentration differences. We have already seen. For example, if you take copper zinc electrode, the concentration of zinc 2 plus ion very near to the electrode will be different from the concentration of zinc ions in the bulk of the solution. Other factors could be the porosity of the materials, okay, the electrode porosity that influence the gas and liquid flow, the permeability of the membrane, changing the ionic flow, and all those things. Reaction over voltage. A voltage difference arises when a preceding or a simultaneous chemical reaction produces another compound. Electron transfer only is what is we are measuring, whereas there is a subsequent chemical reaction that will be also giving rise to over voltage, which changes the operating conditions. For instance, water produced in a hydrogen oxygen fuel cell dilutes the electrolyte, which then causes electrolyte concentration change at the electrode interface. So what is happening if I were to take This is the polarization. That is, the electrode is polarized, negatively polarized. Negatively polarized means you are impressing a negative potential. So now if I were to apply a negative potential and look at the concentration of the ions in the solution, this is the concentration of the ions in the solution. The solution is neutral. The concentration of the positive ions and the concentration of the negative ions will be equal. Whereas very near to the surface, since the surface is, or the electrode is polarized negatively, the concentration of the positive ions will be more. You can see the 3 positive ions are present here, whereas in the bulk of the solutions it is not. 3 is not a correct system. The number of positive ions very near to the electrode is higher than the number of positive ions for the same volume element in the bulk of the solution, for the same volume element. Now the accumulation of the positive cations in the negatively polarized electrode is called the inner Helmholtz layer. We will come to it little later, outer Helmholtz layer. So now this is what is happening. If I were to take an electrode and polarize it negatively, the positive ions will be accumulating very near to the electrode. So this is the electrode, this is the solution phase. The same thing can be put in a capacitor. A capacitor, one electrode is negatively polarized, another electrode is positively polarized. Therefore, it is equal to the capacitor. Here also it is the electrode is negatively polarized. The positive ions are absorbed or accumulated at very near to the electrode. Therefore, this is equal to a capacitance. So now if I were to look at the potential, this is a parallel plate capacitor. I hope you are able to see the 2 plates are this is one plate, this is another plate, where the negative ions are accumulating and positive ions are accumulating. The variation of the electrostatic potential as a function of the distance from the electrode, for example, chi m is the maximum potential, but the potential in the electrolyte, the bulk of the electrolyte is psi s. So therefore, the potential drop takes place. So now situation similar to that of a parallel plate capacitor. So the capacity can be written as C capacitor or Helmholtz capacitor is given by epsilon r epsilon 0 by chi h, where epsilon r is the relative permittivity which is assumed not to vary with distance. E0 is the permittivity in vacuum. Chi x denotes the closest approach distance of the point charges. For example, here or here. The decay of the electrode potential chi m and to chi s is linear. We have already shown this. It is linear, but it will not be linear in a solution phase. If it is a parallel plate condenser, it will be linear. Linear, and CH remains constant in the applied potential. This is the chi s, the distance between the electrodes. Here, the distance between the electrodes can be different. You can see here the distance between the dotted line and the electrode is, whereas the accumulation is away from the dotted line. So therefore, chi h is a variable parameter. This model is called the double layer model. This model has 2 very great deficiencies. One is the interaction with ions in the subsequent layers into the first layer is neglected. What we have assumed here is that the positive ions that are accumulated here, they are not interacting with the ions in the solution. That is not true, because the ions are in a Brownian motion. Therefore, the ions that are accumulating at the electrode surface will be interacting with the ions at the bulk of the solution. So this is another one problem. The dependence of the electrolytic concentration on the accumulation of charges in the double layer has not been taken account. For example, when we said here it is negatively polarized, the positive ions will accumulate here, but these positive ions will accumulate here. For example, we are assuming that it depends upon the potential that is applied, but the positive ions that will be accumulated here will be dependent upon the concentration, the bulk of the solution. For example, 1 molar solution and 0.1 molar solution, there will be an accumulation of charge very near to the electrode, but the extent of accumulation will be different. because the bulk concentration is 10 times dilute. So therefore, if we have to try to take these two parameters. So this is called the diffuse double layer. So you can see that double layer, the double layer is the first layer where the 3 ions are present. In the second layer, there are some diffuse ions. The negative ion also is interacting with the positive ion. So therefore, the capacitance will be varying like this with respect to the distance from the electrode. This is the electrode electrolyte solution. Potential A is the potential representation of ions in the diffuse double layer according to the Goy-Chapman model. Okay, the first model is the double layer model. This is, I hope you are able to see, this is a double layer. There is no diffuse double layer, whereas here it is a diffuse double layer. The B is the variation of the electrostatic potential psi as a function of distance x from the electrode. Here we showed it, it is varying like this. Up to the point, it will be linear. After that, it will be a constant value. But that is only for a double layer section. Whereas if I take this, you can see that there will be smooth transition. Okay. Variation of the capacitance with the potential. Variation of the capacitance with the potential is shown here, showing a minimum at the point of zero charge. Okay, I hope the capacitance is minimum here. This is so the capacity of the diffuse double layer is given by an equation like this. We will not worry about the mathematics of this. We will see later on all these things. So it will all depend upon ER, the E0 permittivity of the thing, the number of ions, and all those things. Please remember, look at these equations. It will have a power. We already told you that all electrochemical reactions will have some terms to the power. We have to define this power and should put the power carefully. We will come to it later on. The capacity varies with the potential systematically with respect to point of zero charge. We will come to it point of zero charge. For example, this is the point of zero charge because the negative polarized electrode and positive charged ions are equal here. Therefore, it is a point of zero charge. We'll look at it. The capacity varies with the potential systematically with respect to the point of zero charge E, and then at that point of zero charge, it will have a minimum value, which correspond to the minimum in the curve. For dilute solutions at 298 Kelvin, you can see here also there is a power concentration to the power half. We will come to it, all of them. The capacitance given here, microfarads, farads per square centimeter. This diffuse double layer can be also considered as, for example, a compact double layer and a diffuse double layer. So therefore, compact double layer will have a capacitance like this, and diffuse double layer will be another term. So therefore, I can say the total capacitance will be the compact 1 over compact capacitance layer plus the 1 over the capacitance of the diffuse Goy-Chapman model. Okay, this is the thing. Now all these models, okay, we will stop at this point. All these models have got very great limitation. What is the limitation is the question. We have, if I were to look at these electrodes, for example, I have put a positive ions in the solution, but I don't have positive ions alone. The positive ions are always surrounded by the solvent sphere. Here it is a metal solution interface only we are dealing. Okay, we are not dealing with semiconductor electrodes. We will be dealing it separately. So even in the metal cases, we are thinking as though the electrolyte, okay, whichever we are using, or the ions are not surrounded by the solvent ions. Solvation is not taken into account. Not only solvation, the solvation is also a dynamic positions. For example, you can see that the cation is surrounded by 4 water molecules. Here the cation is surrounded by 4 water molecules, but not in the same geometry, like that. So, they then you can see the water, the solvent molecules can also absorb on the electrode. Therefore, the ions that are there, they will not give the capacitance. The water molecules also will give the polarity of the water molecules. Water is solvent. Okay, let us assume solvent. The polarity of the solvent also will give you rise to the capacitance. So all these parameters have to be taken. This is the double layer model of the Bockris et al. I do not know whether you know Bockris and the things. Bockris and Reddy, a famous book, 2-volume book on electrochemistry, which is just like a story. You can read that book. So this model is due to them. We will see this later next time. So at this point, I will stop. You can ask any questions you want.